So we're going to talk today about solving first-order differential equations using separation of variables. That's what this video is going to cover. But before we do that, I want to talk really quickly about how do you decide what method to use to solve an ODE. The first thing I advise doing is figuring out what's the order of the differential equation. If it's a first-order ODE, we have a couple methods that we could use to solve it. If it's a higher-order ODE, like a second-order, third-order, we're going to talk about other methods for solving those types of equations later on in the course, so stay tuned for those. For now, we're going to talk about first order. So let's say the answer is yes, we follow this branch down. The next question you want to ask, is the ODE linear? If the ODE is linear, I suggest you try using integrating factors, although you might be able in some cases to use separation of variables, but you will be able to use integrating factors. So if the ODE is both first order and linear, you should think, hey, maybe I'll use an integrating factor here. Now, if the ODE is first order and not linear, the only option you really have at this point is to try separating variables. Okay, so that's what we're going to do today. All right, so yeah, I'm giving it away here that we're going to use separation of variables, but let's pretend that we came across this ODE in the wild and we want to know, should we use an integrating factor, separation of variables, or maybe something else that we're going to learn later on. So we come to our chart, which I have a little mini version over here, and we ask, is the ODE first order? Well, let's look at this differential equation. The order corresponds to the highest derivative that appears. In this case, we have first derivative, so yes, this ODE is first order. So I'm going to go ahead and follow this branch down. Now I want to ask, is this ODE linear? To do that, we want to look at what is going on with the dependent variable. The dependent variable is the one that you're taking derivatives of. In this case, it's y. Now, there's actually a couple nonlinear things happening with y. Let's point them out. Sine of y is a nonlinear thing by itself. Moreover, we're multiplying something with y times its own derivative, so dy dx. This is a super nonlinear thing. This term is a linear term. I mean, it only involves x, so we don't really worry about it. But this term over here is also nonlinear. We have a y cubed that by itself would be enough to be a nonlinear, but we also are multiplying it by dy dx, so extra nonlinear. So is the ODE linear? No. We're going to follow this branch, and we're going to use separation of variables. So let's get started solving this differential equation or finding the general solution. Now, the method of separation of variables kind of is self-explanatory. We want to separate the two variables, in this case, y and x. So we're going to try to put the ODE in the form of some function involving y only, and there's our differential dy, and set that equal to some function involving x only with our differential dx. The reason we're doing that is because we then want to integrate both sides. And because each side only depends on one variable, we can just do our usual integration. So let's go ahead and try to do that with this differential equation. Now, notice that I have two terms that have dy dx. So I'm going to try to get those together and then factor out the dy dx. So I'll have sine of y times dy dx plus y cubed dy dx. So I'm just moving this term over to the left here. And that's equal to e to the 2x. Now that I have my dy dx's kind of together over here, I'm going to factor them out. So I'll have sine y plus y cubed, that whole quantity times dy dx equals e to the 2x. Now I've got this term here that only has y's in it, and I have a term here that only has x's in it. I'm going to go ahead and move this differential over to the right. So I've got sine y plus y cubed dy equals e to the 2x dx. And now I want to integrate both sides. I have separated the variables, so I'm going to go ahead and integrate them, integrate the expressions. On the left here, I've got negative cosine y plus 1/4 y to the 4th. And that's equal to, on the right, this integral is going to be 1/2 e to the 2x plus our constant of integration, c. Now, notice here, in usual circumstances, I would try to solve for y. I'd try to get y of x equals something involving x. But in this case, I've got cosine of y here, and I have a y to the fourth here. So I'm not going to be able to actually solve for y explicitly. What I'm going to do is write down the implicit form of the solution. Really, you could just leave it like this, but it's sort of nice to just have all of the things that have variables on one side and then the constant on the right. So I'm going to do that. But if you decide to leave it in this form, this is also fine. So let's just write this out. I have negative a half e to the 2x minus cosine y plus 1/4 y to the fourth equals c. And that is my general solution. All right, so that was one example. Let's do one more example just to make sure we know what we're doing. Okay, our next example here is we're going to find a particular solution. Let me just back up really quick here. This last example, we found the general solution. So notice I have a differential equation, but there's no initial condition with it. So my final answer has this arbitrary constant, or constant of integration. In contrast to that, this next example, we have an initial condition, so we will not have any arbitrary constants in our final answer. We're going to determine them using the initial condition. Okay, let's go to our flow chart here to make sure we're doing the right things. Okay, so let's ask ourselves the first question, is this a first order differential equation? Well, the only derivative I see here is dy dx, so yes, it is a first order ODE, so I'm going to go ahead and follow that branch. Then we ask, is the ODE linear? Well, I have a thing involving y squared here. In fact, it's 1 over something involving y. So no, it is not linear. I follow this branch down. There we go. I'm going to try separation of variables. Now, I should point out that if you follow these branches, notice that I put the word try, because not every differential equation is going to have an explicit form for you to just integrate, right away. So you try separating variables, but you might not be able to if you come across something that's a little complicated, maybe not as nice. In this case, we will be able to, so let's go ahead and do that. So again, we're going to try to put this in the form of some function involving y only with its differential dy, and some function equal to some function involving x only with the differential dx, because we want to integrate. Well, this one's a little bit easier than the last one even, because if I multiply this on both sides, I will have my expression involving y over here. I'll have an expression involving x on the right, and I can put the differentials with their respective terms. So I'd have 1 minus y squared dy dx equals x squared. But I can move this differential over. So let me actually do that without wasting too much space here. I'm going to move that differential dx over, and then I can integrate both sides. All right, on the left, with the integral of 1 is just y, and then minus the integral of y squared, so the 1/3 y cubed. That'll be equal to the integral of x squared, which is 1/3 x cubed, plus an arbitrary constant c. All right, so let's write out the general solution like we did for the previous example. I'm just going to get all the variables on one side and leave the constant on the other. Again, you don't have to do that. You can just leave it like this. This is the general solution. But I will write it in this form. I'm going to write it in a sort of a funny way, but just because it makes my life easier. I'm going to write it as negative x cubed plus 3y minus y cubed equals c. Now, why did I do that? How did I get there? Well, I've got these 1/3 here, and those are kind of annoying. So if I multiply this whole equation by 3, I'm going to end up with a 3y here, a 1 here, a 1 here, and a 3 times an arbitrary constant. Well, this is still a constant, so maybe it would be better if I called it like C1 or something, but I just left it as C. So that's why here you see I have negative x cubed, that's coming from this term here, plus 3y, it's coming from this term, minus y cubed, it's coming from this term. Okay, so I just multiplied it all by 3. Again, you don't have to do that, but it gets rid of fractions, so why not? Okay, next we're going to apply the initial condition. Okay, so in that last example, we stopped here because we did not have an initial condition. So this was the general solution we were looking for. This time we have an initial condition, so we should figure out what this constant c really should be. All right, our initial condition is that y at 1 is -2. That means I'm going to plug in x equals 1 and y equals -2, and I'm going to solve for c and then plug that back into my general solution. So really, I've got -1 cubed, that's this term here, plus 3 times -2, that's coming from this term, minus -2 cubed, and that's equal to c. So I have -1 minus 6 minus -8, so plus 8 equals c. So really, c is 1. Therefore, my solution to the initial value problem, I'll call it IVP for short, is -x cubed plus 3y minus y cubed equals 1, coming from that constant here from our initial conditions. And that is our solution. Again, this is another example where I have y is in an implicit form, or my solution's in implicit form, because I have a y and a y cubed, and I'm not gonna, go out of my way to get y by itself here. So I'll just leave it like this. All right, that's all for this video. Let me know if you have any questions.